So we'll wait for a few more minutes and then we will start at 7:10. Hello everyone, a very good evening to all. Myself, Vivekananda Naik. I am a PhD research scholar in the Department of Energy Science and Engineering, IIT Delhi. So I welcome you all for this third interaction session on Atomic and Molecular Physics course, which is being uploaded this January 2026 session by NPTEL with course code Energy 26 PH18. Today I will be solving a few sample problems that will be based on week 3 course contents of the atomic and molecular physics course. So before solving a few questions, let's discuss briefly about the concept that were covered in this week's lecture. So if we talk about week 3 lectures, so the failure of Bohr's model were discussed. Failure of Bohr's model, it was discussed. Then that gave rise to Sommerfield's model. Sommerfield's atomic model, and also so that Sommerfield atomic model was based on the concept of quantization, like energy quantization was given by so E is equals to h nu. Similarly, this was given by Planck's Planck's law. Similarly, according to Bohr, it was within that this is nh cross, so the angular momentum was also quantized. So depending upon the quantization condition, also the atomic model was modified. And then there was discussions regarding space quantization, like that was energy quantization and angular momentum quantization, also space quantization, like physical space quantization corresponds to the uh, quantization of orientation of angular momentum. So that was also discussed. Along with that, G-man effect was also discussed. Basically, G-man effect is effect of the magnetic field on spectral lines. So when in presence of magnetic field, a single spectral line that gets split into a number of spectral lines. So this is B equal to 0, this is B equal to non-zero. So all these things were discussed. So we will solve a few problems covering these concepts. So let's start with the discussion. So the question says, question number 1, there is a mixture of ordinary hydrogen and tritium atom. The mass of tritium nucleus is 3 times the mass of ordinary hydrogen nucleus. Then calculate the shift in wavelength of the H alpha line of ordinary hydrogen and tritium. The options are option A 1.45 Armstrong, option B 2.07 Armstrong, option C 0.58 Armstrong, and option D 2.38 Armstrong. So I'll give you a few minutes and then we will discuss about this question. Basically, the question says that the mixture of ordinary hydrogen and tritium. So for ordinary hydrogen, the mass is 1, but for tritium, the mass is 3 times. Then we need to find out the shift in wavelength of the H alpha line for ordinary hydrogen and tritium. So what will be the shift between the H alpha lines between the ordinary hydrogen atom and tritium atom? Why the shift will occur? The shift will occur due to their change in mass, and the, where the mass is coming, that we will discuss. But first, I will let you solve this question, and then we will discuss in more details. So if we solve it, so where the effect of mass will come? So why there will be shift in wavelength of H alpha lines? Because what is the expression for wavelength? It is 1 by lambda equals to r 1 by n1 square minus 1 by n2 square. For h alpha, what are the values? N1 is 2, N2 is 3. Extremely sorry, there are some unavoidable situations. So for H alpha line, N1 is 2 and N2 is 3. So now why there will be shift in wavelength for H alpha line for ordinary hydrogen and ordinary tritium? This is because the expression of R, this R which is Rydberg's constant. So for R, what is the expression? So R will be different for hydrogen and tritium because the mass of tritium is 3 times the mass of hydrogen. So now for hydrogen, 1 by lambda H will be RH 1 by 2 square minus 1 by 3 square, which is RH into 5 by 36. Similarly, for tritium, RT, it will be 5 by 36. So now RH and RT, they are different. So what will be the value of, so now what is the expression for R? So R is M E fourth divided by 8 epsilon 0 square CHQ. So this is for R infinity, where the mass of electron is taken into account, where we assume mass of nucleus is infinite. But if you consider the finite mass of nucleus, then what will be the expression? So for finite mass of nucleus, suppose for hydrogen, what will be the expression for RH? So in that case, there will be mu. Mu is reduced mass, which will be m divided by m plus capital M, where Me is electron and Mh is hydrogen. So in that case, if you talk about the shift, that is lambda h minus lambda t, which will be 36 by 5, 1 by RH minus 1 by RT. So what will be the value of RH? So what is the ratio of RH by R infinity? So it is MP by MP plus Me. So if you convert it, it will be 36 by 5, 1 plus small me by mh divided by R infinite minus 1 plus me by mt divided by R infinite. So if you solve it, it will be 36 m by 5 r infinite 1 by mh minus 1 by mt. So mt is 3 mh. So lambda h minus lambda t will be 30 by 5 into m by r infinity into 1 by mh minus 1 by 3 mh. So 30 by 5 into 2 by 3 mh into me by r infinite. If you put the values, 36 by 5 into 2 by 3 into, so me by mh, the ratio is 1 by 1836. So 1 by 1836 into 1.097 into 10 to the power 7 meter. So if you convert it, it will be 0. Calculate, so 238 into 10 to the power minus 7 meter. So it will be 2.38 Armstrong, that is 10 to the power minus 10 meter. So the correct answer will be 2.38 Armstrong. So why there will be a shift? Because the mass of hydrogen and mass of tritium nucleus are different, and if you consider the finite mass of nucleus, then there will be a shift in the spectral line because the Rydberg constant values will be different for mass of hydrogen and tritium. I hope this is clear to you. Now we move to question number 2. Question number 2 says, assume that there is a one electron atom like hydrogen whose nucleus has charge equal to that of proton but mass is 100 times that of electron. The wavelength of the first line of Balmer series of hydrogen, considering that the hydrogen nucleus is infinitely heavy in compared to the electron, is 6550 Armstrong. Then find the wavelength of the first line of Balmer series of the assumed atom considering the reduced mass. Options are option A 6435.5 Armstrong, option B 6400.5 Armstrong, option C 6615.5 Armstrong, and option D 6735 Armstrong. Basically, there are two conditions. One is hydrogen, another is hydrogen like system. So this is hydrogen for which the H alpha first line of Balmer series is H alpha only. It is 6550 Armstrong, where we have considered R infinity because here it is mentioned hydrogen nucleus is infinitely heavy. But we need to find out the H like atom. So in this case, we have to consider H like atom. But what is the condition? Here the mass of Me by Mh, it is given as 1 by 100. Then what will be the wavelength of H alpha line? So that we will discuss and then we will solve it completely. It's pretty much similar to the previous question, but here the concept is a bit different because here no conventional value is given. Here we have to consider the mass of the ratio of electron and that of the nucleus is 100, 1 by 100, not like general case where it is 1 by 1836. So I'll give you a few minutes and then we will discuss. So if we solve this, so the question was we have to consider two cases. One is a hydrogen nucleus which is infinitely heavy. The another is a similarly hydrogen like one electron atom, but in that case the ratio of mass of electron and nucleus is 100. So the mass of nucleus is 100 times that of the mass of electron. So again, this is first line of Balmer series, which is H alpha only. So like previous question, what will be the expression for H alpha? It will be R infinite 1 by 4 minus 1 by 9, that is 1 by 2 square minus 1 by 3 square, which is 5 R infinite by 36. So this is the first case, and second case is a hydrogen like nucleus which has Me by Mh is 1 by 100. So in that case, what will be the value of lambda? So it will 1 by lambda n, suppose another new nucleus, which will be R infinite divided by 1 plus small m by capital M into 1 by 4 minus 1 by 9. So this is R infinite divided by 1 plus, so Me by M it is given in the question, it is 1 by 100, it is 5 by 36. So now you see 5 R by 36, it is 1 by lambda h. So the lambda h value is how much? Lambda h value is 6550. So we can put that value. It is 100 divided by 101 into 1 by 6550 Armstrong. So what will be lambda n? So lambda n will be 101 divided by 100 into 6550. So if you solve it, it will be 6615.5 Armstrong. So the correct option will be 6615.5 Armstrong. Is it clear to you? So as I can see, two people have joined. So do you have any doubt in this question? I need to explain it once again. Okay, so what we did here, there are two conditions. One was hydrogen molecule, hydrogen atom for which the nucleus was infinitely heavy. Then the second case was a one electron atom, hydrogen like, whose nucleus has charge equal to that of proton, but mass is 10 times, 100 times higher that of electron. So there are two cases. So in one case we will use R infinity, in another case we will use Rn. So Rn in so Rn R infinity, the relation is R infinity divided by 1 plus Me by M. So this ratio Me by M was 1 by 100. So if you put the values, the correct answer is coming out to be 6615.5. So now we will solve question number 3. Question number 3 says calculate the two possible orientations of spin vector S with respect to the magnetic field B. And the options are option A 35.5 degrees, 154.5 degrees. Option B 54.7 degrees, 125.3 degrees, 67.5 degrees, 112.5 degrees, 49.3 degrees, 130.7 degrees. So basically, so this is basically the case of space quantization. So there are different possible orientations of spin vector with respect to the magnetic field B. So that we need to find out. So if you know, in terms of quantum mechanical representation, the magnitude of spin angular quantum number, so the magnitude of spin angular quantum number sorry, spin angular momentum S vector is S vector mod equal to S into S plus 1 root over into H cross. So what will be its Z component? So its Z component, so its Z component will be Sz equal to Ms H cross, where Ms is plus minus half. So now suppose the B is acting along Z direction. Suppose this is B and this is S vector. So there will be possible orientations of S with respect to B. So how we will calculate? So we know what will be the value of theta, the angle between. So if theta is the angle between Sz and S. So Z axis and S vector. Suppose this is theta. Then what will be the value of cos theta? So cos theta will be Sz by S. That implies theta will be cos inverse Sz by S. Then depending upon the two Sz values, because Ms has two values, so Ms is plus half minus half, so theta will be cos inverse Sz by S. That implies cos inverse Sz is Ms h cross divided by S into S plus 1 h cross root over. So for Ms is equals to plus half, theta will be cos inverse half divided by, so we know S is half, so half into half plus 1 root over, this is plus minus, so it will be cos inverse plus minus 1 by root 3. So theta will be 54.7 degrees and 125.3 degrees. So the correct option will be option B, 54.7 degrees and 125.3 degrees. I hope this is clear to you. Now we move to question number 4. Question number 4 says, consider hydrogen-like atom where the orbital electron is replaced by a particle of mass 250 times that of electron and charge same as that of electron. Calculate the ionization energy of the new atom. Options are option A 3400 electron volt, option B 3250 electron volt, option C 2992 electron volt, or option D 2051 electron volt. So here we are considering about hydrogen like atom where the electron is replaced by a particle of mass 250 times that of the electron and charge is same that of the electron. So the mass of the particle is 250 times mass of the electron and charge is same. Then what will be the ionization energy of the new atom? So I'll give you a few minutes and then we will discuss. So if you want to calculate the ionization energy, first we need to calculate the expression for energy. So what will be the expression for energy? So energy expression is equals to m z square e fourth divided by 8 n square h square epsilon 0 square. So this is the expression for energy. Now for this hydrogen like atom, this Me will be replaced by mu, and here we have considered infinity means the mass of nucleus is infinite, but this is not the case that is given here. So you have to consider finite mass of nucleus. So in that case, what will be mu? Mu will be small m capital M divided by small m plus capital M. So it will be 250. So here m is not mass of electron, it is 250 times mass of electron. So 250 times Me into 836 times Me, which is mass of proton, because nucleus is same, but the electron is replaced by an heavier particle, which is 250 times mass of. So 250 plus 1836, it is 2086 Me. So if you calculate, mu will be 220 Me. So then what will be the value of energy? So one thing we need to consider, what was the value of energy for hydrogen? It was 13.6. So that was Me e fourth divided by 8 epsilon 0 square h square, where we have put z equal to 1 and n equal to 1. Because it is for ionization energy, it will be the first level or ground state, which is n equal to 1, and for hydrogen like atom, for hydrogen atom, z is 1 only. So this is 13.6. Now the new atom, for new atom, suppose EP, it will be mu e to the power 4 divided by 8 epsilon 0 square h square. So in that case, this is 2, this is 1. So if you divide 1 by 2, so EP will be mu e to the power 4 divided by 8 epsilon 0 square h square into 8 epsilon 0 square h square divided by me e to the power 4. So sorry, it gets cancelled, e4 gets cancelled, it will be mu divided by me. So mu is 220 me, it will be into into so it will be 220 me divided by me into 13.6, which will give you EP is 13.6 into 220, which is 2992 electron volt. So the correct answer will be option C, 2992 electron volt. I hope this is clear to you. Now we move to question number 5. So question number 5 says an electron microscope is operated at 5000 volt. Calculate the de Broglie wavelength associated with the electron beam. Consider the relativistic mass correction. Consideration of relativistic mass correction is not required. So here we will not consider relativistic mass correction. And the options are option A 0.122 Armstrong, 0.154 Armstrong, option C 0.25 Armstrong, and option D 0.173 Armstrong. So how we will calculate? So we need to find out the de Broglie wavelength associated with the electron beam. So what is the formula for de Broglie wavelength? Lambda is equals to h by mv or h by p But when we are considering that the energy it is gaining is when it is getting accelerated through a potential difference of volt, then what we can say? So we know E is equals to, so 2E by m is P, sorry, uh, E is equals to 2P by m. So E is equals to 2P by m, sorry, E is equals to P square by 2m. So E is equals to P square by 2m, and that E we can put EV is equal to P square by 2m. That implies P is 2m into 2v root over. So if you put all the values, because here H we know H is 6.62 into 10 to the power minus 34 joule per second. 30. So this is, so if you put all these values, we know mass of electron. Uh, then there is a formula which says lambda in Armstrong is equals to 150 by V root over. So here V is 5000 volt. So lambda will be 150 divided by 5000 volt. It will be 0.173 Armstrong. So the correct option is option D, 0.173 Armstrong. Now you move to question number 6. So question number 6 says, in Sommerfeld model, if n is the principal quantum number and k is the azimuthal quantum number, and if n equal to 1, then what will be the value of k? Options are option A 0, option B 1, option C 0 and 1, or option D 1 and 2. So according to Sommerfeld theory, k is less than equal to n. It was given by Sommerfeld. But for n equals to 1, so what will be the value of k? K will be 1 and less than 1, that is 0. So k will be 1 and 0. So there will be two values of k, 1 and 0. But 0 is not possible, because when k will be 0, but when k is 0, then we know the value of k and n, they basically show the major radius and minor radius. So according to Sommerfeld's theory, we can write k by n equals to b by a. So when k becomes 0, then a by b becomes infinite, so which is not possible. So k can't be 0, because if k becomes 0, then the uh, length of this minor axis of the orbit, that will become 0. So in that case, the path of the electron will be a straight line. So when B becomes 0, then the orbit in which electron is revolving, it is a straight line. So which is not possible. So due to that, the value of k, it will not be 0, it will be only 1, because when k equal to 0, the orbit will be straight line, and that straight line, it will pass to the nucleus, because according to the Sommerfeld's theory, the electron is revolving in an elliptical orbit with the nucleus is present at one of the focus points. So when the orbit becomes a straight line, it will pass to the nucleus. So according to Sommerfeld's validation, for k equal to 0, the value will be only 1 and 0 is not possible. So the correct option is option B, that is 1 only. Then we move to the next question. The question number 7. Question number 7 says the rest mass of an electron is m if it moves with a speed of 0.905 c, where c is the speed of light in free space. Then what will be the relativistic mass of the electron? So options are option A 2.35 m, option B 1.89 m, option C 2.05 m, or option D 3.25 m. So the rest mass of electron is m. What will be the mass of the electron if it is moving with a speed of 0.905? So this is basically relativistic mass correction of electron. So what will be the relativistic mass? M divided by 1 minus v square by c square root over. That implies m divided by 1 minus 0.905 square root over, which is 2.35 m if you calculate. So the correct option will be option A. Then we move to the next one. The question says, in Sommerfeld's model of fine spectra of hydrogen, if n is principal quantum number and k is the azimuthal quantum number, then the condition for the electron orbit to be circular is, options are option A n greater than k, option B n less than k, option C n equals to k, or option D the shape of orbit is independent of the relation between n and k. So just we discussed in the previous question that the relationship between n and k is given by k by n is b by a, where b is the length of minor axis, sorry, where b is the length of um, uh, minor axis, and a is the length of major axis. So it is minor axis, a is major axis. So for circular orbit, b equals to a, so in that case k by n will be 1, or k will be equal to n. So the correct answer is option C, n equals to k. So for n equals to k, b equals to 1, and the orbit becomes circular. I hope this is clear to you. This was pretty much simple. Now we move to question number 9. So question number 9 says, according to Bohr-Sommerfeld model for fine structure, how many transitions are possible for principal quantum number n equal to 3 to n equal to 2? Options are option A 1, option B 2, option C 3, or option D 4. So according to Bohr-Sommerfeld model of fine structure, how many transitions are possible for principal quantum number n equal to 3 to n equal to 2? So these are the 4 options. I'll give you a few minutes to think about this question, and then we will discuss what will be the correct answer. So, according to Summerfield's theory, what will the value of k? K will be less than equal to n. So n equal to 3 to n equal to 2. So for n equal to 3, k will be 3 to 1. 0 is not possible. So 3 to 1 is the acceptable values. Then for n equal to 2, k will be 2, 1. So what will be the selection rule? So the selection rule is delta k is plus minus 1. So now let's arrange the labels. So this is n equal to 3 according to Bohr, but in Summerfield's theory that gets splitted into three values depending upon the three labels depending upon the k values. So k is 1, 2, 3. Similarly n equal to 2, that gets splitted into two labels. K is 1, k is 2. So now let's discuss about the transition. So from 3 to 2 the transition is possible, but from 3 to 1 the transition is not allowed, because for 3 to 1 the delta k will be 2. So here delta k is 3 minus 2, 1. Here is 2, so it is not allowed. Then from 2 to 2 is not possible, because delta k is 0, which is not allowed. But for 2 to 1 is possible, which is corresponding to delta k is 1. Then from 1 to 2 is possible, minus 1. Then from 1 to 1 again it is not possible. So 1, 2, 3. So there are three possible transitions from n equal to 3 to n equal to 2. So the correct option is option 3. Sorry, option C, that is 3. I hope this is clear to you. Now we move to question number 10, which is the last question of today's interaction session. The question says, the de Broglie wavelength of an electron accelerated by v volt is 0.5 Armstrong. Find V. Ignore the relativistic mass correction. Options are option A 300 volt, option B 3000 volt, option B 6000 volt, option C 9000 volt, and option D 10,000 volt. So this question we had already discussed similar type of question where the voltage value was given to us and we needed to and we had to calculate the value of wavelength, but here wavelength is given de Broglie wavelength and we need to find the value of B. So these are the four options. I'll give you a few minutes to try to solve this and then we will discuss. So as we have already discussed, the expression for de Broglie wavelength of electron, if lambda is in Armstrong, it will be 150 divided by V root over, so 0.5 equals to 150 divided by V root over, it is 0.25 equals to 150 by V, that implies V equals to 150 into 4, which is 600 volt. So here I think the options were wrong. So the correct option is option B, 600 volt. With this, we come to the end of today's interaction session. So I hope the questions that I have solved today will help you to solve the course assignments. With this we will stop today's discussion. Thank you all.